Good morning, budding chemists. Imagine walking into a supermarket where every item, from bread to shampoo to batteries, is dumped randomly in one giant heap. Would you survive that shopping trip? Of course not. Organic chemistry is the same. There are millions of organic compounds, and without classification, studying them would be chaos. We organize them mainly based on their carbon skeleton, whether it is acyclic or cyclic, and also by their functional groups. This helps us predict physical properties, chemical reactivity, and even how to name them systematically using the IUPAC rules. Once classified, patterns like homologous series and isomerism become clear. Think of it as making a mini periodic table for the organic world. Let's start with the simplest group, the acyclic or open-chain compounds. Picture them as long ropes of carbon atoms, either straight or with small side branches. Examples include ethane, written as CH3 single bond CH3, ethene, written as CH2 double bond CH2, and ethyne, written as HC triple bond CH. When chains branch differently, they form isomers. For example, N-pentane is CH3-CH2-CH2-CH2-CH3, while isopentane has a branch at the second carbon. Both have the molecular formula C5H12 but different structures. In real life, these acyclic molecules fuel your LPG cylinder. Propane and butane are classic examples. So, straight chains may look simple, but branching brings a huge playground of diversity. Now imagine bending those chains into circles. That gives us cyclic compounds. One type is alicyclic compounds, like cyclohexane, where 6 carbons join in a ring but behave like alkanes. Another is aromatic compounds, the superstars, because of their delocalized pi electrons. Benzene, written as C6H6, is the famous one, stable and flat, and used in petrol, perfumes, and dyes. But sometimes rings include other atoms like oxygen, nitrogen, or sulfur. Those are heterocyclic compounds. Furan has an oxygen in the ring, pyridine has a nitrogen. Such heterocycles form the basis of many drugs and even nucleic acids in our DNA. So next time you see a benzene ring, remember it's chemistry's wedding ring, holding reactions together with strong delocalization. Here's a challenge. If I say the molecular formula C2H6O, could you tell me its behavior? Not without the functional group. Functional groups are like ID cards. For example, when the group is hydroxyl, written as -OH, you get an alcohol, such as ethanol. When it is aldehyde, written as -CHO, you get ethanol. When it is carboxyl, -COH, you have acetic acid, the sourness in vinegar. Some compounds even carry multiple groups, like hydroxy acids which have both alcohol and acid properties. Functional groups control reactivity, so knowing them is like reading the molecule's job description. That's why two formulas with the same atoms can behave like chalk and cheese. It's all about their functional tags. Now let's talk about homologous series, chemistry's version of a family tree. Each successive member differs by one methylene group, which is -CH2-. For example, methane is CH4, ethane is C2H6, propane is C3H8. Notice each step adds 1 carbon and 2 hydrogens. These compounds have gradually increasing boiling points and solubility differences, but their reactivity is nearly identical. Their general formulas are also neat. Alkenes follow CnH2n+2, alkenes follow CnH2n, and alkynes follow CnH2n-2. So whether it's cooking gas, camping fuel, or gasoline, you're really dealing with close cousins in the same family. Homology keeps order in the chaos. Time to play detective. Suppose we have a compound with molecular formula C4H8O2. What class could it be? Step 1. Check possible groups. It could be an ester or a carboxylic acid. Example 1. Methyl acetate, written as CH3C double bond O-CH3. Add sodium hydroxide solution and it hydrolyzes to give sodium acetate plus methanol. Example 2. Butanoic acid, written as CH3CH to CH2C double bond O-OH. Add sodium bicarbonate and you'll see bubbles of carbon dioxide gas along with salt and water. Same molecular formula, but one is an ester and the other is an acid. This is functional isomerism in action, two identical outfits with completely different chemical personalities. So, to wrap things up, organic compounds can be sorted into open-chain acyclic, closed-chain cyclic, allocyclic or aromatic, and heterocyclic when non-carbons join the ring. Functional groups act as their ID tags, determining both reactivity and naming rules. Homologous series bring predictability, where each member differs by a -CH to -unit. And as we saw with C4H8O2, classification also helps us spot functional isomers. Think of classification as the periodic table of organic chemistry, a grand organizer that makes millions of molecules manageable. Chemistry is not just random equations, it's the hidden logic behind fuels, medicines, plastics, and even food. I hope you enjoyed today's journey through the organic map. Until next time, keep spotting those functional groups around you. They're everywhere from your soft drink to your shampoo.